countries, so I'm really glad that I can talk to everybody now. So let's start talking about solar resource assessment, and this is the overview. Obviously there are some definitions about DNI, which is the main fuel for CSP and CPV. Measurements, how can we predict solar radiation and DNI in particular, model data for the world, variability in the solar resource, which is very important, frequency distributions as a function of climate, and can we trust TMY time series, TMY being the typical meteorological years. And finally, well, can we do local measurements for large projects, and should they be done for how long? So first, some definitions. As I said, the fuel for CSP and CPV plants is DNI, which is direct normal irradiance. And this is the direct radiation coming straight from the sun's disk, and at a normal incidence, which means that if you want to track the sun with a 2-axis tracker, you will get the full DNI coming from the sun. There are actually two slightly different definitions for DNI. The theoretical definition is the irradiance received from the sun's disk only, and that can be calculated, or the irradiance from the sun's disk plus some circumsolar diffuse irradiance within a cone of about 2.5 degrees around the sun center. And this is the practical definition because that's what the instruments can measure. And so in the context of this presentation, we will talk mostly of the second practical definition rather than the first one. But in the next webinar next week, we will actually go into more details about what this circumsolar diffuse contribution can be. So DNI is essentially what a 2-axis tracking concentrator can use fully. 1-axis trackers like parabolic troughs will get somewhat less, and next week we'll look at this a little bit more. So CSP systems are thermal systems, so they can use the complete solar spectrum. And in that case, only the broadband DNI is of any interest. In the CPV case, obviously solar cells have some pronounced spectral sensitivity, so even though the broadband DNI is what matters most, we can look into spectral effects. So these are specialized topics, spectral effects, circumsolar radiation, will be covered in more detail in the next edition of this webinar. Now, measurements. DNI can be measured directly or indirectly. Obviously, the main or the most interesting measurement is the direct measurement. And this can be performed with different kinds of instruments. The first one is a reference instrument, which is called the active cavity radiometer. It's mostly a laboratory instrument. It's not made really for continuous monitoring, and it's very expensive and very difficult to maintain, but it's very important for calibration. Most instruments in the world are thermopile power heliometers. Those are robust field instruments. They are mounted on a tracker, so they actually track the sun, and this is why they can sense the DNI, because their sensor is always normal to the sun rays. The most common models are the A-Play NIP and the Kipanzonen CHP1 now. Third type of instrument is the rotating shadow band pyranometer, or RSP. This is also a field instrument. It is using a silicon sensor, so it has a fast response. It doesn't need a tracker because it's on a flat surface, and it measures both global and diffuse, from which direct is obtained by subtraction. It doesn't use as much electricity or maintenance as thermopiles, but because it's a silicon sensor, it needs corrections for temperature, cosine errors, and spectral sensitivity. So you know, there are pluses and minuses in everything. In the bottom part of the slide, you see the different types of instruments, and here we go. So the active cavity here, two types of thermopiles, and two types of rotating shadow bands. Now, I said also there's a different way of measuring DNI, which is an indirect method, and it is basically using one pyranometer for global horizontal irradiance, which we usually call GHI, and another similar instrument but with a fixed or tracking shadow band or shadow disk for diffuse horizontal irradiance. And then we can obtain the instantaneous DNI from this very important formula that probably you are very well aware of, which is simply the difference between global and diffuse divided by the cosine of the zenith angle, which is the angle between for the sun between the zenith and the actual position. So this method was very common in the past, and actually it might still be common in many countries, but the problem is that typically it has a lot more error or uncertainties than in direct measurements. So that depends also on the type of instrument you choose and the type of sunshade for the diffuse measurements. I will cite a lot of references, so you can actually use those documents for more information. And again, some pictures of those instruments. On the left side here we have pyranometers to measure global irradiance, another pyranometer to measure diffuse, and you see the shadow band here, which is fixed but has to be moved every few days. Another setup for diffuse measurement, but in this case it has a shade ball which is tracking the sun, so it just provides this little shade on the instrument. And another kind of setup with the same kind of tracking balls and a different pyranometer to measure diffuse. Calibration is very important. You cannot have a good measurement if the instrument is not well calibrated and also very frequently calibrated, which means at least once a year. So there are modern methods of calibration for both power heliometers and pyranometers, and that is done against the World Radiation Reference, and these methods are explained in that book here, book chapter actually. And we see here on the right side a picture of the World Radiometric Reference in Davos, Switzerland. And this is actually a set of different reference instruments. They are all active cavities, and those instruments have been chosen because they were extremely stable. This setup is only providing measurements once in a while. It's not permanent, so once in a while they do comparisons with standards from different countries. Actually, there was such a campaign earlier this year. Usually it's in the fall in Davos. So all the reference instruments from different countries in the world come there and recalibrate their own references. That's how it's done. And the WRR is actually providing a reference to the absolute watt. DNI is measured in watt per square meter, so we need a reference to the watt, and these instruments being electrically compensated, they measure an electric current, which is easy then to obtain the watt. There are performance issues. The Eblay NIP appears sensitive to a small daytime bias and or thermal effects, which makes its response vary during the day with smaller but higher relative errors early in the AM or late in the PM. So there's a new paper on this issue being now published. And also GNI measured with the rotating shadow bands must be corrected for various problems. And those two papers here provide empirical corrections for those instruments. So what can we expect? What accuracy can we expect from those measurements? Well, typically if you use a good instrument like a pyrheliometer in the field with good calibration, good maintenance and everything, you can expect 2 to 5% uncertainty in the field. This can be quite larger if you are using an indirect measurement with a conventional setup. And so be careful about that, because it can be a relatively high uncertainty then. What are the sources of measured data? Unfortunately, in the world, there are not too many sites measuring DNI with very high quality instrumentation and also which provide publicly available data. So there's one international network of research class station, and that's from BSRM. I provide the web link for that, and you see here the map of the station. There are many stations in the US and in Europe, and a few others elsewhere, even in Antarctica. So there are only a few stations which are relevant for CSP and CPV application because they are in very clear conditions. Obviously, this network is not made for us, solar energy people. That's made for mostly atmospheric physicists and climatologists and everything. But we can use the data. All the BSRM data are measured at 1 minute intervals with very high quality instruments and maintenance and quality checks and everything. So for the moment, that's the best data we can get in the world. In the US, there are only 4 high quality stations that have accumulated more than 25 years of DNI data, and there are 3 of them are in Oregon, Hermiston, Eugene, Burns, and the 4th one is in Golden, Colorado, which is where NREL, the National Renewable Energy Lab, is actually measuring radiation with a lot of instruments. Another point which has to be noted is that data from national weather services are usually not in the public domain, and that's why we don't have too many measurements of DNI available, unfortunately. So because of that reason, we have to rely on modeling. So we have to look into more details into what radiative models can do. There's a general typology in this book chapter, and it also proposes various quality criteria, validation methods, performance and ranking metrics. So from a general standpoint, to calculate DNI or any irradiance anyway, atmospheric scientists use radiative transfer models. They evaluate the fluxes wavelength by wavelength. But obviously this is quite too cumbersome for general use in the engineering world. So for that kind of application, there are more a lot simpler broadband models that are used. And unless specific spectral effect for PV or CPV is needed, then broadband models are okay. For spectral effects, we will see next time how we can do that. The very simplest models calculate DNI with a daily or monthly time step, but this is only good for rough design purposes. But for any serious resource assessment, hourly or sub-hourly data are necessary. So that means that we have to use a little bit more involved models. To obtain those time series at the hourly or sub-hourly time steps, there are essentially two different methods. And there's a physical method or semi-physical method in which here we first have to calculate the solar position, which means the zenith angle from date and time. The air mass is calculated from zenith angle. The actual extraterrestrial irradiance is also calculated from date and time. So this is the easy part. Now we also need to get some atmospheric data for the input data to the models, and those atmospheric variables are essentially pressure, which is related also to altitude, ozone, water vapor, aerosol optical depth, and a few other things. And those are the variables that affect the clear sky irradiance and DNI more specifically. There are also environmental variables that you need to collect, such as the ground albedo, which is the reflectance of the surface. And also shading might be important, especially if there are mountains around or buildings, or even self-shading from other concentrators, for example. So with all this information, you put that into some model and you obtain the clear sky DNI and the clear sky global irradiance, and obviously also the clear sky diffuse irradiance. Then this is good if you are interested in clear sky only, but generally there are some clouds too, so you need to provide a model with some cloud data. And then at this point we have actually two different possibilities. Either you use airport observations based on human observations of clouds from the ground up, or actually the reverse, meaning observation from satellites which observe clouds from above. And in some cases these satellites and retrieval methods provide cloud detection, which means a type of cloud, altitude, cloud optical depth, a lot of physical optical properties. With all this, now you can actually calculate the cloud transmittance, and multiplying this by the clear sky values, you obtain the all sky DNI and all sky global and all sky diffuse. And you obviously do that every hour or every 15 minutes or every minute if you want, and you get your time series that can be very long, and usually it is as long as you can get cloud data or the atmospheric variables. Now a second method is more like an in-between physical and empirical. It has actually a little bit of both. So we start again from the same thing, the clear sky calculation is essentially the same, but the cloud data is different. Now in this case the models only use satellite imagery of the radiance. It means the reflected energy coming from the surface or the clouds, and this is translated into some kind of cloud index and this is empirically related to the surface global irradiance, horizontal irradiance. So there's an empirical function here that relates global irradiance to the cloud index, which is itself a function of cloud cover. And with this modeling, you obtain the all sky global irradiance. Now, how do we get DNI? We need an empirical model which relates DNI to GHI, global irradiance, and then finally you obtain your all sky DNI that you want. Some example of semi-physical or physical models: Mach3 in Canada, that was done about 25 years ago. MedStat in the US. Those two actually used wholly human cloud observations at airports. The problem is that in North America there's no more of these. All the airports have have been equipped with automatic instruments. They are called ceilometers, and they just measure the altitude of clouds just above. So it's a little bit more difficult now to use that kind of information with those models. They were not made for that. So the trend now, and especially in the US, is to obtain is to use physical models based on satellite information. And one such example is GSEP. And this uses cloud retrievals. It is now working to obtain global irradiance. DNI is still in progress. Other examples of semi-physical or empirical models: the Perez model from SUNY Albany in the US, DLR in Germany, 3-tier in the US, Heliosat, the Heliosat method from different countries in Europe. So all these actually use this empirical function between DNI and GHI. And that is the weak point of these models. There has been research for about 50 years since the pioneer work of Liu and Jordan, and still there's no accurate or universal method to do this. And this is the method, the empirical part of this that I was referring to. Some example of what the problem can be. Here we have a plot of the measured 1 minute DNI measurement at NREL in Golden, Colorado, for 3 years of data, in 2 different empirical models that are used very commonly in this kind of application. Here, modeled by Herbs and by Perez, and as you can see, Herbs is providing you with a lot of overestimation for DNI. Perez is certainly better on this point, but still there's a lot of scatter, and specifically here for the Perez model. Now, same kind of comparison, but in this case in the case of snow on ground, and I was referring to the ground albedo. In this case, snow has a very high albedo, and it might generate some overestimation again. In this case, it's a comparison between the Herbs model and the Reindl model. They are all empirical, and they are all based on some other stations data, and so that's why they don't really fit all the possible locations in the world. So you have to be very careful about this. Now, what can we expect from model clear sky DNI? Well, in this case, because we don't have clouds, it's relatively easy. If we have good input data, the atmospheric part of that, meaning water vapor, ozone, aerosols, etc., it's relatively easy now to obtain very good performance. So far the REST-2 model is unsurpassed in performance, and it can predict DNI within the uncertainty of high quality irradiance measurements. Obviously it's only if we have the good atmospheric data. So some references on that, and some examples of validation results using REST-2. In this case here we have a comparison for an air mass of about 1.5 at different locations in the world with very different climates, from Mauna Loa, which is very clear, and Solar Village, where there's a lot of dust aerosols, and some other typical dust storms here. So you see in general, I would say almost all the time, we are within 5% of the high quality measurements. The issue, of course, is to get the atmospheric data at 1 minute resolution, which is very difficult. But at least what that shows is that the model is itself good. So if you have good input data, you have good output data too. This is a cumulative frequency distribution for 1 minute data, 1 minute results from Mauna Loa, Hawaii. Mauna Loa is a very high altitude site at 3.4 kilometer altitude, so it's very clear. It's above most of the atmospheric layer, if you want. So that's why you can get irradiances up to 11 and 50 watts per square meter. And we can see that the REST-2 model is very close to the measured values for what is important here, above 800 watts per square meter. So after a lot of years of experience, I would say that to obtain accurate model DNI predictions, the chosen model must be as physical as possible. We have to be very careful about empirical methods or too simple algorithms. An example is the old ASHRAE model. It was published in 1972, but it's still used by many engineers, and especially in the building, energy, and simulation applications. It's a very, very simple model where DNI is only obtained as a product of a coefficient A by an exponential of another coefficient and the cosine of the zenith angle. So you have only two coefficients, which are monthly constants. So you have two pairs of 12 values, and that cannot be more simple than this. But because it's so simple, you don't have any information on the current atmospheric state, water vapor or aerosol or anything, and that's why here you see for 3 different sites the kind of scatter you obtain in the results. So it's not very good. Whereas when you use REST-2, you have the burden of getting all these atmospheric inputs, but you also get a lot better accuracy. So now let's go to another issue. We found last year actually, we found that the Perez-Souni model had an important issue in some climates, and that was called the Eugene syndrome, where actually every winter we had extremely high errors for DNI and obviously GHI too, and that was systematic each year for actually 8 years. And that happened mostly in Eugene and some other locations where it's very cloudy and there could be some snow on ground. So there was a problem with the algorithm. Since then it has been corrected, but the problem is that the published data are not corrected yet for that kind of stuff. It doesn't affect CSP CPV because it's only for very cloudy regions, fortunately. So for CSP it's okay, but obviously for other application it could be important. So this is another thing that we have to be very careful about. So the availability of high quality inputs is crucial, and this is the main difficult part in general, because we have to avoid spatial and temporal interpolation as much as possible, and specifically for clouds and aerosols. So we also discovered that using monthly average aerosol data, which is most generally the case, that leads to significant errors in the model DNI, and then incorrect frequency distribution. This has been showed in these papers, and some example of that here in a very clear site in Desert Rock in the southwest US, where the cumulative frequency distribution is not correct. And here another result for Tamanrasset, Algeria, which is another very clear site, and the different sources of DNI data sets disagree a lot compared to the measurements, and this is all related to the aerosol problem. What are the other factors affecting DNI? Of course, the first one is always cloud. But then for CSP CPV, normally you will be in a region where there are as little cloud as possible. So the next important things are aerosol. Aerosols is measured with the aerosol optical depth, AOD, and this is a very important parameter. Then water vapor, which is measured by the precipitable water, here PW, ozone, pressure, NO2, and air mass is also a very important thing. That's the pure geometry. So about aerosols, they are the main cause of DNI extinction under cloudless skies. And for example, if you were to build a CSP or CPV plant in some areas affected by dust, like the Sahara, for example, or some parts of Asia, you would have this issue that going from a clean day to a very dusty day, your DNI will drop a lot. So depending on air mass here, on precipitable water, but it has a very small effect compared to AOD. So AOD is a key parameter here. And so also it's important to note that DNI is about 3 to 5 times more sensitive to AOD than global irradiance. So it's relatively easy to obtain global irradiance data. Oh, Fernando, I would need that movie if you can. Okay. Well, this movie shows you the variation of the aerosol optical depth during a year over the globe. And you see the dark areas are where the aerosol is very intense. And usually it's because of either dust storms or biomass burning, things like that. Pollution also, of course. So as you see, it changes all the time, and it can be very important in some areas. Thank you. Okay, so other sources of aerosols are the volcanoes, and as I mentioned before, the dust storms. Here we have a big dust storm from the Sahara, and those dust storms can reach the other side of the Atlantic, as well as the Asian dust storms can reach the US from the Pacific. So all these sources actually emit aerosols, and this is always variable from one day to the other. So we need to be well aware that if you want to have a CSP or CPV plant somewhere, it has to meet some criteria, and I summarize them into how to get the maximum solar resource in DNI, requiring 5 minimums. Clear skies, obviously, minimum cloudiness, minimum haze or turbidity, minimum water vapor, minimum latitude, because you want the minimal air mass as possible, and also high elevation, which will decrease your pressure. So with all that, you would find the perfect site for your CSP CPV project. Unfortunately, there are not that many perfect sites in the world. The best sites are, we call that the Sun Belt. There's no clear definition for this, but let's say that you need at least 5.5 kilowatt hours per square meter per day, or which translates into a total annual of 2000 kilowatt hours. So maps of this kind, this is from NASA, SSE, maps of this kind show you where your best location could be, and then you have to look into more details, of course. Model data, there are some free data sources. I just mentioned NASA SSE for the world. You see all those sources here. There are also maps and geospatial toolkits, which means tools that you can use with GIS software generally. And there are also now commercial data sources. I list all those I'm aware of at this point. And finally, there's a new handbook for solar resource applied to CSP, and this is freely available from NREL. Now let's have a look at a typical DNI resource map. This one has just been released by NREL. We, SCS, we provided the aerosol data for that. The cloud data were provided by the Meteosat satellite, and all that was input into the SUNY model from Richard Perez. The results show that there's a high resource in the Himalayas here, but this is not really practical, of course, because of the mountains, altitude and everything, and it's far away from the urban centers. So elsewhere, the DNI resource we found is limited by strong haze and also monsoon cloudiness. Here a satellite image from that part of the country, where actually we find one of the main interesting area for CSP and CPV, but all over there's strong haze all the time. Same thing for that part, it's even stronger, and you can see another image from satellite where all this haze shows very clearly. And so this is certainly not the best place for CPV or CSP applications. So you must be very careful about this. Haze is actually killing DNI. Now differences, there are now many resource maps and resource data sets, and there are differences between them. We have good sources. We have a lot of sources now, which is good, but which one to choose or which one to believe in is a little bit difficult sometimes. We have to look into this more carefully. So typically we find 5 to 10% differences over some regions with good density of weather stations. In other cases, like if you are away from these stations, the differences can be a lot more. We have found in different parts of Africa in particular very large differences. We see now two different maps, one from NREL Swera for North Africa, and the same part with the same colors from NASA SSE. And you see there are large differences between them. So this is actually, this recently happened in Abu Dhabi, where the resource was calculated and did not correspond well to the measurements. Now we have done this study for Kenya, comparing the resource map from NREL and from DLR. And Kenya is sitting on the equator. The northern part is a little bit sunnier, certainly, but still the differences for those two data sets are quite important at some locations. And in this case here for Baringo, it goes from there's a 2x difference in those two data sets. So this is a difficulty in some countries. So what can explain these inconsistencies and large disagreements? Well, cloud data certainly is part of that. They use widely different aerosol data sources. They might use long-term monthly averages or daily data, which is another source of problem. The use of empirical algorithm, sometimes their performance is degraded in some areas, but you don't know that in advance. There's a lack of validation against ground truth, and this is normal because such data is rare in some countries. Or if they are used, they might be of low quality and you don't know it. There are some tweaking sometimes, and it's not always clear what has been done, and so it can improve results in some areas and actually degrade them in others. And so also there's some lack of scientific consensus on the modeling techniques and quality control methods. In the case of commercial vendors, they might not tell you what they do, and their method is relatively proprietary, so you cannot be sure of what is being done. So to remedy this situation, the International Energy Agency, with the task 36 and Solar Paces, have launched research projects to validate or benchmark the various data sets. So this is still ongoing. I participate in this task to identify, obtain high quality DNI measurement data for the whole world. So then we can test different data sets. Now, the connection with the finance world. So far we have been looking at the technical side of this. The solar resource is variable, and obviously this affects a lot of things, but in particular this affects the cash flow of any project. So there are some, the variability in revenue means that reserve accounts are to be made for debt service and avoid problems. And that's why all these financial institutions require so-called bankable data, and they require probabilities of to exceed some minimum power production and revenue, and they are basing their lending or their they are trying to see what is the best way to obtain revenue and avoid risk. So they need to assess the risk, and that's why they require some probabilities of exceedance. The incorrect evaluation of this risk may lead to various problems. Well, some cases, if it's not correctly made, they can reject a good project. So how can we do this kind of calculation? What we find is that on a short-term DNI, the short-term DNI variability is relatively important, of course. DNI can go from 0 to 1,000 watts in a matter of a second or a fraction of a second, and vice versa. So this is not easy to take into account, and especially if you measure solar radiation with on a hourly time step. We have here an example of a typically partly cloudy day in Oahu in Hawaii, where we see here a lot of cloud coming. I assume there are cumulus clouds, fair weather clouds, and the effect of this is particularly around noon is that your global irradiance in green goes very high, actually to 1654 watts per square meter, which is about 25% more than the extraterrestrial irradiance at that moment. The extraterrestrial irradiance is the gray line here, and the orange line is DNI, and you can see that there are also some effects from the clouds on DNI, more limited than on a global, but still a little bit. The short-term DNI variability is no problem if the plant's operation tolerates DNI fluctuations, including having no DNI at all and then DNI coming back, which would be the effect we just saw in the previous slide. But there are CSP plants that cannot operate below some threshold DNI because it's not interesting. There are too many losses, thermal losses, for example. So can these transient effects be correctly accounted in the daily, monthly, or annual resource if DNI is not measured fast enough? This is an important question, and actually it is only being a start of new research projects on this, so there are not definite answers. Let's see what we have with this typical day in Hawaii. I considered different thresholds from 0 to 300 watts per square meter, and various measurement time steps from 3 seconds, which is the original data, 1 minute, 15 minutes, 1 hour. And why 15 minutes? It's because some commercial data vendors provide data at 15-minute intervals. The hourly time step is more common, but as we found out, especially for that day, if you go from 15 minutes to 1 hour, you don't know exactly what you do, and you can lose your short-term variability in the process. So the other conclusion is that going from 1 minute time step down to 3 seconds, you don't gain much in accuracy. So the main gain is to go from 1 hour to 15 minutes and hopefully to 1 minute. So this topic needs further research, and hopefully in the future we'll set up an optimal data time step for and we have here what happens in Eugene, Oregon. I mentioned Eugene before with the Eugene syndrome. So these are the measurements since the very early, since actually 1978, when the measurement started. And you see that if we accumulate the first year of measurement, we calculate the average on the second year and so forth. It takes about 13 years to reach plus or minus 5% of the long-term average DNI. It takes a lot less time for global irradiance, about 3 years. But can you wait 13 years before knowing your long-term solar resource? It's obviously certainly not interesting for most CSP and CPV projects. Here we have another plot with the yearly differences from the long-term average in both DNI and GHI. So the conclusion actually is that very short measurement periods, 1 year or less, are absolutely not sufficient for serious resource assessment. So we need to do something else, and there are special techniques now that we can use to correct the long-term modeled data using those short-term measured data. And this is what is usually done
Chris.
for bankability reports.
This is impressive.
I think, Fernando, if you want, I could stop here so that we have time for questions.
How far we can go in the determination of solar resource and how difficult it is, how many things are to be considered. So something that seems to be so basic actually is extremely complex and definitely requires expertise. So thank you to let us know about these features. Very well, so you're invited to submit your questions. You have probably already done. However, based on the presentation, you can type your questions in the window, submit a question. So they will be stored here, and we will try to moderate them. Okay. Yes, sure. This.
May I first say something? Obviously, I had too much material. I had too much material this time, so everything else will be provided next time.
I sent the first question.
Hopefully, we'll have
from Amit Jain,
a lot of time for that.
For India,
so
where
if there are questions about the variability,
data,
it will be partly done next time.
What do you suggest is the way to get bankable data? Thank you.
Well, actually, I showed a map of India, which has been released very recently. There are maps for DNI and global, and I would say there was not much measured data, obviously, and that's the main problem. Poor AOD data is correct also, and that's why we worked on that and provided NREL with better AOD data than was done before.
Okay,
now, bankable data,
so
I would say there are some if you cannot find
well, I think
public
quite
domain
related
data,
to the
there
previous
are
one.
some commercial
If you want to
vendors
purchase DNI data,
that
which
will
sources
certainly be
or
very happy to
company
provide
would
you with
be
that.
the best service? Well, this is a difficult question. Thank you.
Well, yeah, and I don't want to go too far on that, but there are, I listed actually the companies, the commercial companies that I knew of, and I think there were 8 or 10 or something like that. So you have a choice. You have to know that not all of them provide data for the whole world. So depending on for what region you are interested in, that will probably determine
So, a
which
simple
company to
question:
go.
how expensive are pyranometers and
So I
radiometers?
would be happy to
So, can you
answer
provide
that
us with some light
offline
on
if you want
this?
for more details. Um, Obviously, price is a matter of quality or performance. There are very expensive ones. It depends also if you need a tracker, and for example, if it's for a specific project, a weather station, do you have electricity on site, for example? How do you connect to the data logger and everything? So the answer actually varies a lot, but you certainly don't have anything for less than $2,000, for example. That's probably a minimum price. Usually, people actually do not buy a single instrument unless it's a rotating shadow band, because it provides you with 3 components: direct, global, diffuse. If you need the regular thermopiles,
Great.
there will be
Thank
one
you,
instrument
Chris.
per component.
So,
So that could be more
let's
expensive.
see.
Usually thermopiles are a lot more expensive than
Well, there is
silicon-based
a
instruments.
question on. Could you further
Again, we
explain
can
why
talk
deny
of that
is greater than
offline.
global radiation? I don't know whether is it right. I let you.
Yeah. Yes. Yeah. No, it's a good question actually. You probably remember that equation I provided, where DNI is equal to the difference of global and diffuse horizontal, and that difference is divided by the cosine of the zenith angle, and that cosine value can be obviously less than 1. It is always less than 1. So the ratio is can be a lot more than global, and especially under clear skies. Diffuse is normally relatively low, so the global minus diffuse is close to global. You divide that by a number that is less than 1. It can be 0.5, for example. So in some cases, especially around noon, or I would say, excuse me, around in early AM or late PM, DNI will be a lot more than global horizontal. Global horizontal is affected by the cosine of the zenith angle, whereas
Okay,
DNI
great.
is not.
So
And that's why
another question
DNI can be more than
from
global.
Dave Rogers.
It's just that
Perhaps
DNI is
we will
measured
address
on
this
a
question next time. Okay, so
perpendicular plane to the sun,
let's
whereas
see.
global is measured on
Do
the
site
horizontal,
assessments
fixed.
in industrial sites. Can you use data sources, for instance, local pollution measurements, LIDAR for gaseous or particulate pollution concentrations, for example, weather bureau measurements, do not measure local plumes. Okay, so please.
Yeah, that's a tough question. I would say it's doable. It's certainly feasible from a theoretical standpoint, but who can do that actually and with what kind of data is a difficult matter. So ideally you would need instruments on site, because, and especially in an industrial environment, you know, those plumes can change all the time. So, for example, on a weekend days, there might be no plume at all, and then in the weekdays there can be a lot of pollution. So everything changes very rapidly. Using LiDAR is a good idea, but you have to process that, and it's not obvious, and it's very specialized. So there are a lot of very tough technical issues there.
Chris. So
but as I said, you know, there can be some
when measuring DNI
very
with
sophisticated model to do that, but it's not mainstream in the solar energy business, I would say.
Thank you.
Well, there's no typical uncertainty because it depends so much on the instruments you choose, and also the shadowing and the correction to the shadowing. So you should read the paper I indicated. I published, I think, 2 years ago in Solar Energy.
Right.
This is relatively the latest I know about
question. What has been your
but basically, depending on your conditions, the uncertainty could be from 5 to 15%.
Which ones are
maybe more in the early AM and late PM. In my experience, MODIS is closest to the ground truth, and that's, you know, I compared different satellite sources for AOD. There are different satellites. In my experience, MODIS is closest, but it doesn't mean it's perfect. Actually, there's usually a bias, but that bias can be corrected relatively easily if you do some performance assessment against ground truth. So far it's the best source. The problem is that there's also a lot of missing data points, and especially in very highly reflective areas such as the Sahara or snow and everything like that. They don't provide you any data in these areas, so you have to switch to some other sources for those places. That's the difficulty with MODIS. I want to go back to that question. There was I published a paper last year in Solar Energy and about how to obtain AOD data for the world, and it's relatively well explained there. I'm not sure what you mean there. Yeah, indeed, Davos is the world reference. That's where all the labs in the world come with their instrument and intercalibrate, if you want, and be sure that they have their own calibration correctly done. Then they go back to their country and they use those secondary reference standards to calibrate all the instruments in their country. So that's the way it goes. So I'm not sure about inter-comparisons between calibration labs, because normally there's no problem. They do this inter-comparison at Davos every other year. In the meantime, because they are very stable reference instruments, they shouldn't change too
we
much.
have another question.
Like certainly less than 0.1%.
Using only the
drift.
annual
So
average value of DNI.
Normally, all the calibration labs in the world should be on the same page and on the same reference.
Thank you.
Well, the problem is that the annual average, you don't know exactly how it has been obtained. You would have to look a little bit more into that. Was it really measured, and for how long? You know, was it only for the last year, or for 5 years, or for 20 years? And that would change the picture because of the variability that I just started touching on. Now, was it measured or was it modeled? This is another issue. You have a lot of uncertainty in both, actually, so you have to be careful. But certainly, it's a start. If you see that your annual average DNI is 8 kilowatt hours per square meter, you should be in a safe place. If it's on the contrary, if it's only 2 kilowatt hours per day, then you might have a problem, and certainly not a good place for CSP. Now, I mentioned this story about the Kenya data that I found, where according to NOL we have a very good site for a CSP, and according to DLR it's a very bad site. So which one do you believe? It's another issue around that question. Latitude is not really a problem. You can have very high DNI at high latitudes, although generally, have you seen on the maps, it's around I would say 35 degree north and south within that band. So you do not need any latitude correction. If the measurement or the modeling is done correctly, your value should be okay at any latitude. The main question behind that is how good is your annual average? How has it been obtained, and has it been verified? Also, the annual average may mask some problems in the monthly data, and in some cases you need also monthly data, because you have usually more radiation during summer than winter.
Thank you very much,
so
Chris. So
all
I
this
think
will affect your
hereby
design.
We will adjourn. Thank you very much,
because it will affect also the quantity of electricity, of energy you can provide during those months.
Chris, on the continuation of solar resource assessment. So visit the webpage on Leonardo Energy to check the program. Well, I'll let you say goodbye, Chris.
Thank you so much to everybody, and hopefully we'll see or actually hear you again next week. Thank you. Have a good week.